Okay, 5 seconds. 3, 2, 1. Okay, please put your pencils down to be fair to everybody, that everyone has the same amount of time. So now if you could just kind of pass them in and get them over to me. All right, what did y'all think? What'd you think? Obviously not everybody finished, but
How many points do you get off if you forget that plus C?
if you forget plus C, you miss the whole problem.
Really?
No. But there are some professors that will do that. Like in a class after this, that might happen. Don't be surprised if that happens. All right, do you want to discuss it? Yes? Okay. Make sure I'm recording. Yes. All right, so the correct substitution for number 1 is what? Everything under the radical, right? U is x squared minus 3x plus 1. And that is because the derivative of that is 2x minus 3 dx, right? And we almost have that right here. Right, there's this right here. If we just multiply this by 2, right, then we would get 4x minus 6, wouldn't we? Yeah. So we just multiply both sides by 2. 2 here, 2 there. So we have 2 du is equal to 4x minus 6 dx. That marker's dying. And so now we can replace, right, this right here, we'll replace this. And then this right here will be that. God, this one's dying too. So, yeah, that's why people leave them in here. They never throw them away. All right, so this integral can be rewritten how? 1 over square root of u. That whole thing is u. And then everything else that I circled here is 2 du. So I'll put the 2 out here and then du. And that's really 2 times the integral of u to the negative 1/2, just rewriting it using exponents. And now we just take the antiderivative with power rule. So this is going to be 2, which comes for the ride. And then we add 1 to that. And so we get 1/2. It's 1 over 1/2, which is really another 2. U to the 1/2 plus c. So that's 4. U to the 1/2 is the same as square root. So square root of u, but what was u? All that stuff. I'm moving a little fast because, well, yeah. But okay? Questions? All right. How about the next one? What's the correct substitution? E to the x. So what you need to see here is that this is e to the 2x, right? You need to be comfortable with the idea that this is really e to the x squared. Because if you do something to a power and then raise it to a power, you multiply these two, and 2 times x is 2x, right? Okay, so you have to see that. I believe that happened in the homework at some point. Okay. So u is equal to e to the x, not e to the 2x, e to the x. Then du is itself, right? And there it is, right there, sitting right there, staring at you. So the derivative is right there, right? And I'm going to replace e to the x right here with u. So what do I get? 1 over 1 plus u squared. That should look familiar. And then du is the part that's circled. Arctan. Arctangent of u plus c. So this is arctangent of e to the x plus c. There we go. So I was asked the question, what happens if you forget the plus c? I'll probably take a point off only because it's not completely correct. You know, 1 point out of, I mean, like, there's only 2 questions here. So if you forgot plus c, you probably get like a 96 if you forgot plus c on both of them. All right? But that's because I'm very lenient with it. Later on down the road, if you take another class, math class, they might say if you miss the plus c, it's completely wrong. It's totally up to the professor. So I've had professors do that. So, all right. What if you forget what?
Because of the first you get the plus C. Like, you get the arctangent one, and you get the plus C.
I'm not sure I'm...
Is that an extra point?
He's saying if the answer is wrong, but you add the plus C.
Oh, do you get a point? Do you get any points for just having plus C? Yeah, I mean, for showing up, it is partially correct. So I guess you could look at it like, you know, if you get every problem wrong and you just write plus C, then you could get 4 points here on this test. You won't get a 0. It's very difficult for me to take off. It's very difficult for me to take off all points for a problem. Like, you have to leave it completely blank for me to take everything off. All right, I hope that that quiz went well for you. I'll see how it went. Did anyone else try something different on that second integral? Did anyone try e to the 2x as your substitution? So were you having issues with it? Yeah, you see why now? Okay, so it actually comes up more often than you would think that e to the 2x appears in problems. You just have to always remember that it really means e to the x squared. All right? Okay, we are starting a new day. They don't have the projector completely fixed, but they have a workaround. So now I can project my notes up here until they come in and try and fix it, and they'll probably ruin it. They'll probably break everything. So we are going to start a new section today, integration by parts. And in my notes, I explain where the formula comes from, but I actually love to just walk through it step by step, you know, just to start, all right? So far what we can do is, if we're recapping, we have x to any power, we can take the antiderivative. If we have something we recognize, like secant squared, we know that that's the derivative of tangent, so we can go backwards from that. If we have an integral where we see something and its derivative in there, we have this basic u substitution. And we even saw that even with that, sometimes you make a substitution that doesn't even look that natural, and it still works out. So now we've got all these things in our toolbox, right? So now we have this new technique, and it's called integration by parts. Here's where it comes from. Do I need to write integration by parts? I guess it will. Integration by parts. And you'll see me abbreviate this IBP. From here on out, I don't want to have to write that over and over and over. So here's where it comes from. It actually is a formula, all right? The difficulty with this formula is just knowing when to use it, all right? Because you can't use it on everything. The integral has to be a certain way for it to work, all right? So here's where the formula comes from. Let's say that I have two functions. I could say like f of x, and let's say I have another function g of x, all right? Two different functions. So as an example, let's say I have two functions like x and sine x. Those are two functions of x, right? Okay, now just so the notation works out properly for me, let's call this function f, let's call it u, and let's call this function g, let's just call it v. Is that all right? Okay, now if we take the product of u times v, that means you're going to take these and multiply them together, these two functions, and multiply them. Then in Cal 1, we learned that if we wanted to take the derivative of this, that we would have to bring out the product rule, right? So the product rule would be, and this kind of depends on how you were taught. I always teach my students, if you have a product, it's the derivative of the first one times the second one plus the derivative of the second one times the first one. That's the way I teach it. But you could flip these over. You could even flip them around like that, and it's all the same formula, right? Everyone agree with that? Yes. Okay. Now, this is going to kind of seem ridiculous because I just took a product and I differentiated it, right? Now I'm going to integrate it, which should undo it, right? So let's see what happens. If I integrate, if I do the antiderivative of this left side, and then I do the antiderivative of this right side, like that, I'm going to take the antiderivative over here. Now, this is with respect to x. I didn't put dx in here, but it's with respect to x because these functions were with respect to x, all right? But I'm just trying to get to a formula here, so that okay if I write like that? Okay, so what happens if I take u times v, I take its derivative, then I take its antiderivative? I should just get u times v, right? Agreed? All right. Now over here, if we have a plus in between two things, and I'm trying to find the antiderivative, can I do the antiderivative of each one individually? If there's a plus, yes, I can, right? So do you agree that this turns into the antiderivative of u prime times v plus the antiderivative of v prime times u? Do you agree with that?
Yes.
Okay. Well, this is an equation, right? This is an equation. And so with equations, I can add things to both sides, subtract things on both sides. I can multiply both sides by a number, right? These are the rules. So I'm going to choose to do something, and just follow me through with this, all right? I'm going to take this term right there, that whole integral, and I'm just going to move it to the other side, which will make it negative, won't it, when it goes to the other side? So here's where I'll be. I'll have u times v minus the integral of vu prime. Now notice I took these and I just switched their order because it's multiplication. You'll see why in a second. And then equals, what's still over here on the right hand side? Integral v prime u. So can I write that u v prime? Same thing, multiplication can flip. Does anyone know what that property is called when you have multiplied factors and you just reverse their order? It's called a commutative property, not commutative, commutative property of multiplication, all right? We're always allowed to flip multiplication around. So this is all the same formula? Now what I'm going to do is I'm just going to rewrite it again, but I'm going to put this stuff like on the other side of the equation. Just tell me if you believe that this is still true. Almost did it. Vu prime. That's the same equation, right? Okay, one more thing, and we're done. When I say v prime, I mean take the derivative of v, don't I? Yeah. I'm going to write that with a slightly different notation. I'm going to write dv instead of v prime. Is that all right? And then I'm going to write uv minus integral v, and instead of writing u prime, what do you think I'm going to write? Du. Okay, there it is. This is the integration by parts formula. Now, you might be looking at it going, what the hell, right? Like, what is this? This is weird. But let's analyze what this equation is saying, all right? This equation is saying that, hey, look, let's say you have multiplication of two things over here, all right, inside of an integral, which has been problematic for us, hasn't it? Trying to undo a product, antiderivative, has been problematic. This says, look, if you have some function, let's call it u, then you have some other function, which we're just going to call dv right now, that you can rewrite that integral as u times v, which will be whatever you see there, that's u, right? Just rewrite it. There it is, u. Yes? And then what's v? If this is dv, then, and this is v, then this is actually the what? The antiderivative of that, right? So if I take this function, write it, and then this one, take its antiderivative and put it there, then subtract from it a new integral, and now look what happens over here. I have v here. What did I have over here? dv. So this is the antiderivative of v, right? And then this right here is the derivative of this one. What? Okay. Why? Why would you do this to yourself? Why would you sit here and take an integral that looks a certain way and rewrite it as a new integral, right? Why go through all this effort? Here's why. Here's why. Because in the original integral, I'm working with u, right? In the new integral, what will I be working with? Du, right? In the original integral, I'm working with dv, right? And in the new integral, I'm working with what? It's antiderivative. So what's happening here in this formula is that you have an integral that you're stuck on, right? You look on the inside of it, you're like, crap, I've got some things in here being multiplied. You ask yourself this question, would it be easier for me to work with the integral if I could take the derivative of this in the antiderivative of this? Because this new integral might be easier to work with, all right? What we have done here, this process here, is, and I'll never forget Dr. Richardson. Thank you, Dr. Richardson, when he was the one who showed me integration by parts. He stressed that this whole formula is all about transferring. I think I'm misspelling transferring. Is it 2 R's? It's 1? Who cares, right? Transferring the derivative.
I know, this is a complicated.
This is why I'm not an English major. Okay? Too many rules that don't make sense. I before E except after C. Nah, that's a bullshit rule, right? That doesn't always work. Okay. So is it 2 R's or 1? It's 2 R's. It does, but I just want to know, and I'll forget.
You're fine.
So we are transferring the derivative. We're transferring the derivative within the integral. I didn't have a derivative on U. Now I do, right? Here I had the derivative on V. Here I don't. It's like they switch places, right? Now how can this be valuable to us? How could that formula actually ever make life better for us? Well, let's take an example. Okay, so take a look at this one. Look at that one right there. All right, so we start going through the things that we know. All right, well, this is not just a power of x, right? Can't do that. It's not something I recognize. Like, it's not something from Cal 1 that I know that's the derivative of something. Basic substitution. Can I plug something in and then do I see its derivative? Like, do I see something in its derivative? Do you? I mean, I don't. You could say x, right? Maybe. What would happen? We never did this last class, but what would happen if you make a substitution u is equal to x? Okay, the derivative would be 1. So can I just put dx? And then let's rewrite the problem. What would we get? This would be integral x is what? U. And then sine of what's x? U. And then dx is du. All you have done is rewritten the same problem. It's just now you replaced all your u's with x's. Congratulations. Right? So this is a pretty useless substitution, isn't it? Okay. So I've exhausted what I know at this point. Like, I don't have a technique to attack this, right? But let's look at this. If I come in here right now and I recognize multiplication here, right? If I call one of these u and the other one dv, then in the new integral, I'm going to be working with v and du. So let's see. What if I call this one my u, and then everything else that you see, your dv? Do y'all see that? Yeah. In the new integral, I'm going to need to work with v. V would be the antiderivative of sine x dx. What is the antiderivative of sine x dx? Negative cosine x, right? Okay. I don't mind seeing negative cosine x in the new integral. But this is the beauty of the formula. In the new integral, I'm going to have du. And if u is x, what's du? 1. So the only thing in the new integral is what? Just the cosine, right? Negative cosine, but just a cosine, right? It's like the x vanishes. Make sense? Yes or no? Does that kind of make sense? So what I'm going to do now I could have picked it the other way, and I think we should look at that. What would happen if instead I would have chosen this to be u, right? And then these two guys together right there to be my dv. Does that make sense? Yeah. In the new integral, I'm going to have v, which is the antiderivative of what? X dx. What's the antiderivative of x dx? 1/2 x squared? Right? That will be in the new integral. And then what will also be there? Du, right? What's the derivative of u? Cosine x. Now, look at this. That would be in the new integral, wouldn't it? Do you really want to integrate that? Doesn't that look worse than what we started with? I mean, the first one was just x sine x, and now we have 1/2 x squared cosine x. That doesn't help, does it? But when we did it the other way, we essentially used the transferring of the derivative to kill the x off, didn't we? It's like we're going to kill the x. And the other function integrated up to cosine, we can handle it, right? Isn't that nice? Okay, so let's do this problem. Oh, I forgot the little cute little name that you can, the little acronym we can use to, it's not an acronym, is it? Not really. It's just a little jingle that you can use to help remember this formula. All right, and it is ultraviolet minus voodoo. Ultraviolet minus voodoo. Someone showed me this and I've always remembered it, so don't get upset that this little jingle doesn't include the integral sign in it, but this is the way it works. Ultraviolet minus voodoo, all right? Ultraviolet minus voodoo, right? If you can remember that, you'll remember the formula, all right? You just don't forget the integral, okay? So technically it should be ultraviolet minus integral voodoo. All right, how do we do this? All right, so we're going to have kind of a systematic approach to this. All right, here we go. So let's act like we're starting this problem from scratch now, all right? Come in here, I don't recognize it, it's not a power of x, basic U substitution doesn't work. Maybe integration by parts will work, but I know that in integration by parts, I'm going to have to differentiate one of these and integrate one of these, right? I think I really like the idea of differentiating x because it's going to get killed off, right? And I don't mind integrating sine. So the way I do it is I make a table. And in this table, every single time, I will put u here, and I will put dv down in the bottom right-hand corner. Those two pieces of information, I have to choose what I'm going to call u and what I'm going to call dv. So for me, I'm going to call the u what? I wanted it to be the x, right? Because in the new integral, du is nice. Now that forces dv to have to be everything else that's there. Sine x dx, yeah? Okay, now we're going to complete the table. And the way the table works is that the functions are up top and the derivatives are on the bottom. So du, I'm differentiating, I'm coming down to get the derivative, so that'll be just dx, right? And then from dv, I go up and I integrate that. You realize that this step right here to here is an integral. Like you have to integrate that. And sometimes you actually have to do that on the side and like do an integral. And then come back and slap the answer in here. But I think this is a clean enough antiderivative that we can just go directly to this, right? Okay, that's it. Once you've completed the table, you just go to the formula. So this will equal, according to the formula, u times v, right? U times v, which is u, and here's v. So if I multiply those two together, I get negative x cosine x. No integral on this, right? It's just u times v. Then what? Minus the integral, and now v du, which will be this diagonal right there. You're going to multiply across that diagonal, which for us will be negative cosine x times dx. Now, what do you think I'm going to do with that negative that was inside that integral? I'm going to take it out, and that negative that was already out there is just going to become a plus. Yeah? So we get negative x cosine x plus the antiderivative of cosine x dx. And see, this integral I'm comfortable with. The antiderivative of cosine is sine. So I can go negative x cosine x plus sine x plus c. There it is. That is the antiderivative of x sine x. Wow. Is it really? Check it. Okay, we have a product right here, don't we? Let's check it. And this one I don't have a product, right? So I can just do this one separately. Let's do the product rule there. The derivative of this is -1 times this plus derivative of cosine x times plus, yes? Okay, what do we have here? Negative cosine x. Negative negative is plus, right? Plus sine x times x is x sine x. And then this is plus cosine x. And these cancel, and you get x sine x. What an incredible formula that this is. It really does open up what we can do now, all right? Is everybody clear with the idea that you have to choose the u and the dv? And that you could pick them wrong? Yes?
It's any consolation, you spelled transferring correct.
I did. Thank you. Thank you.
It is 2 R's.
That's a victory for me. Yes?
So when you integrated the dv, you don't need the plus c at the top.
Oh, good question. When I did right here to here, why didn't I do plus c? Because I know at the end of the day, this is an antiderivative, and it's going to have a plus c anyway. So I could have carried that plus c with me the whole time, but all it would have done is at the very end had a plus c. So when in the table, when you go up here, ignore the plus c. And just remember at the end, add plus c. That fair? Okay, good question. Isn't this exciting? Yeah. Isn't it kind of cool how that formula, that entire integration by parts formula just comes from the idea of the product rule? That's all it comes from. There's no like voodoo magic. Oh, I guess there's voodoo in it, but VDU. So it's u dv equals uv minus integral v du. All right. I'm just going to put that for reference. All right. Now, what we're going to do now is I have a whole list of problems that I want to do. Okay? A, B, C, D, E, and F. And I think it's important for me to go through each of these because they each contain kind of their own little element to them that makes them unique. They all require integration by parts. But first one's going to be very basic, all right? So let's start with that one, which is almost exactly the problem we just did. Except now I have a 10x inside the integrand, or inside the sine function. So we want to integrate x sine 10x dx. All right, so we look at it, we don't recognize it, it's not a power of x. Basic u substitution doesn't work. But now that I'm armed with the integration by parts formula, I know that if I have a product of two things, one of them I can call u, the other one dv. In the new integral, I'm going to have du and v, right? So what do you want to choose for u? X, right? Awesome. And dv, then by default, has to be everything else there. Sine 10x dx. All right. Let's get du. Du is what? Dx. So yes, it's 1, but if you have 1, make sure you put that dx there, all right? It's 1 times dx. And now we have to go and integrate to go up to v. So we got to go from here up. And we talked about this at the end of class last time, that if you have this trig function and you have a linear function inside of it, you're going to have to account for that with some sort of scaling out in the front. Okay, so what's the antiderivative of sine of 10x? Negative 1/10 cosine 10x. See the end of class last time if you have any confusion as to what I just did here. We did talk about that. You okay with that? All right, so we have our table filled out. So now we're just going to do ultraviolet minus voodoo. So what is ultraviolet? It's u times v, so across the top here. And let's just kind of put it in an order that makes the most sense. How should I arrange my things here? Maybe negative 1/10, first, like get your constant out there first, and then x, and then your cosine 10x. All right, good. That's u times v. Minus integral voodoo, which is the diagonal. Do you see why it's important to have the dx here? Because when you do this times this, that gives you the dx that needs to be in the integral. All right. So let's do it. It's negative 1/10 cosine 10x dx. We're in business. Because I don't mind integrating cosine, right? Now that constant out front kind of bothers me. So I'm going to pull the negative 1/10 out. It's going to make it a positive 1/10. And then I'm going to integrate cosine of 10x dx. These markers are fading away fast here. Go ahead. Don't wait for me. What you got there? Ooh, that's a good one. What is the antiderivative of this? 1/10 sine 10x. But we already had a 1/10 out there, didn't we? So negative 1/10 x cosine 10x. And then we have plus the 1/10 that was already out there, but the antiderivative of this is another 1/10 sine of 10x plus c. See, there's my plus c. I don't want to forget about it. And these two come together to be 1/100th. And we're done. We could check it, but we won't. There we go. Questions? Comments? Concerns? Complaints? Let's take a look at the next one. So that one on my notes, I called that problem a basic integration by parts. Now, one that's not so obvious. Integral arc sine of pi x dx. So I want you to look at that. I'm going to go grab some markers, because these markers, well, there's like hundreds, but they're all half dead. And plus, I want to give you an opportunity to think about this one. I think so, unless you want them. No? Okay. I wish we had chalkboards. I miss chalk. Chalk is fun. All right. Think about it. The hint is that this is integration by parts. Oh, we're dancing, we're dancing. Okay, what is the big issue here with this one? There's no like product between two functions, right? Like the last one, x sine x, yes? We could choose one, but there are actually two functions here. Right there. So here's what we could do. Tell me if this makes sense. We could let u be the arc sine of pi x. But in the new integral, it's going to be its derivative, isn't it? And I better be able to take derivative of that, which I can, right? But that means the only option I have for dv is dx, right? And I better be able to integrate that. But remember, that's 1, right? Can you integrate 1? It's going to go back up to x, isn't it? Okay, now be careful. This will never happen in integration by parts. You will never have this situation. Okay? Like, this would have been the only other possibility that you could have done. Right? With what's up there, like this is the only two options, yes? This will never happen. You always have to have a dx here. And you would never want to take the derivative of the derivative. All right? Because you would wind up getting what? Well, this is like 1, right? So what would the derivative be? It would be 0. And then you'd have to integrate this, right? And what would the antiderivative of this be? I don't know. It'd be the integral of this. I don't know what that is. That's the original problem, isn't it? So it's a disaster. This is not going to work. But that will. You understand? Okay, so let's do it. du. What is derivative of arc sine of something? 1 over square root of 1 minus what's in here squared, right? How about pi squared x squared? Can I do that? Am I done? No. Times the derivative of what's in here, right? Which is pi. I'm just going to slap that pi up top. Where that 1 was, I kind of snuck it in there. And then we have dx, don't we? Yeah? Okay. And then when we integrate up here, we just get x. Now, I think at this point you might start getting a little bit nervous because you know that your new integral is going to be this diagonal, right? Your new integral is going to be this times this. And that right now looks like a mess, doesn't it? But it's not going to be, all right? Just follow this through. Okay, according to integration by parts, this is ultraviolet. So this times this. Minus the integral of this times this. I'm just going to write it out. X times pi over, whoa! I don't know what happened to my pi there. 1 minus pi squared x squared, and then dx. Yeah, I got a little crazy there. Yeah, do you see it? Okay, so here we're all happy, ultraviolet. Like, yay, we don't have to do anything with that. This is intimidating to look at. I could pull the pi out, couldn't I? Because that's a constant, so I could do that if I wanted to. Let me go ahead and do it, because maybe it'll just make your life a little easier. If I pull the pi out, then this is a 1, yeah? Okay, so you look at that integral, and this is a basic U substitution. So now we're back at like square one. We have a new integral. So you start with all the different things we know again, right? So if this is a basic U substitution, for this problem, what is the basic U substitution that I'm going to want to use? 1 minus pi squared x squared, the whole thing. We're going to grab that whole thing under the root. Why? Why the whole thing? Because what's its derivative? Du is, well, derivative of 1 is 0, yeah? And then what's the derivative? Let's see, the negative pi squared is a constant, isn't it? So I have negative pi squared. I should have just grabbed some different color markers. I grabbed like 5 black markers. All right, negative pi squared comes for the ride. What do you think? Going to work? Pretty bad. Negative pi squared. And then what's the derivative of x squared? 2x. So how about I do this? Minus 2 pi squared x. Yes? dx? So we're looking for something in its derivative. Do we have the derivative over here? I'm off by a constant. You see that? What do I have here? I have, well, I don't need the 1, but I'll go ahead and close it too. I have x dx, don't I? And that's x dx right there. So all I have to do is divide this out on both sides, and I will have x dx. Hold on. 1 over negative 2 pi squared du equals x dx. Okay, now, yes?
So when you get derivative of 2 pi, it's stayed at 2 pi.
This right here?
Yeah.
That is a constant. Pi squared is a number, isn't it?
Yeah.
So if this would have been negative 10x squared, you would have just said negative 20x derivative, right? Because 10 is just a number. Well, pi squared is just a number, right?
Oh, okay, I see.
You sure? That's why I did this example with a pi. I like to put pi in here because it really forces us to understand, like, it's just a number, so we treat it a certain way. Yes? Are we good? That means I can rewrite that integral. Okay? I can rewrite this. So look, it's almost like I'm doing separate work on the side here. Okay? So it's kind of like I've started over, and I've said, look, hey, everyone, I'm trying to do this integral. X over root 1 minus pi squared x squared dx. And when I did that, I did a basic u substitution. And when I do my u substitution, this becomes the integral of what? Let's see. This goes together, right? So don't worry about that. So I'm going to have 1 over root what? U, right? U was this. And then times x dx, but x dx is all of this, right? So let me write it as negative 1 over 2 pi squared du. And what can I do with the negative 1 over 2 pi squared? Just pull it out. And 1 over root u is really u to the negative half. And now I'm ready to find the antiderivative of that using my power rule. And when we take the antiderivative of this, we're going to get 2u to the half. 2 times u to the 1/2. Or 2 times the square root of u. So negative 1 over 2 pi squared times 2 square roots of u plus c, but I'll get the c at the end, okay? Okay, oh, the 2's canceled. Great. All right. So this is really negative 1 over pi squared square root of u. What was u? 1 minus pi squared x squared. All right, that's it. This right here, I'll do it at the end. This right here is just that, right? So now we're ready to get our final answer put together. See, I'm like doing scratch work within scratch work within scratch work, right? I'm doing things off the side a couple of times to get back to this. Remember, I'm just the messenger. This is the subject, okay? All right, so I'm rewriting this. And then I have minus pi. Don't forget that minus pi was there, right? Minus pi. And then times, now this thing, right? So this is times negative 1 over pi squared, square root of 1 minus pi squared x squared plus c. I'm looking out at you and I can see these looks of, you're just like how beautiful this must look to you. Like you're really seeing the beauty in this, yes. Is that the look? Am I interpreting that look correctly? There we go. So I just made the minus minus plus right here, and I cancel one of the pi's. Now, if we take the derivative of this, we should get that. Right? That's what should happen. What do y'all think? Come on. I need to see I want to know what you feel.
What happened to the 1 over pi squared?
Right here?
Yeah.
Okay, so I just cancel one of these pi's. Because that pi's on top, this is pi squared. Okay. Yeah. It is, I was telling you this subject builds on itself quickly. And you can see with this integration by parts problem, you have to be comfortable with substitution, right?
Yeah.
All right, I'm going to check it. And I will stop checking these, all right? At some point, we're just going to have to trust we did it right, all right? But it's hard to believe that the derivative of this is that, right? I mean, at the very end, when I take the derivative, I should just get that. I have my doubts. Let's see. I have a product rule here, right? And then here, this is plus, and then I'll have to take derivative of that. So quickly, derivative of this is 1 times, right, derivative that's 1 times that. And believe it or not, everyone, that piece right there should be the only thing left when I'm done with everything else, okay? So that's this times this, or derivative of this times this, plus the derivative of this. What's the derivative of this? 1 over square root of blah, 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 times pi, chain rule, and then times x. Pi x over square root 1 minus pi squared x squared. Yeah? That's a derivative of this times this. Okay, done with product rule. Plus, now, derivative of this, right? Now the 1 over pi comes for the ride, times, what's the derivative of the square root of something? 1 over 2 square roots of that something, right? Times the derivative of what's inside, which we did this already. It was negative 2 pi squared x squared. No, we took the derivative of the x, so just x, right? Yeah? Okay, now what happens here? 2's gone, one of the pi's are gone. So all I'm left up here with is what? Pi times x? Pi times x over this root of this junk, and it'll be negative, right? Negative pi x over this junk plus pi x over that junk. This is positive, that's negative. They're gone, you're left with the first term. Yes, 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 yes. Going backwards is much more difficult than going forward. Yes? All right. So that was the second example. Let's look at something different. I mean, it's still integration by parts, but let's look at something different. So the first one I said, hey, this is a basic integration by parts. The second one, not so obvious. And it was not so obvious because we didn't have two things, right? So I picked one of them as u and the other one was dx, was dv, right?
Yeah.
Okay, this one, repeated integration by parts. T squared cosine, what's that? Beta. So beta is a constant that we don't know. Okay, so treat beta like the letter A or the letter B. It's some constant that we don't know. So if we ever need to take the derivative of beta by itself, it's 0. But if it's attached to the variable in the function, it just comes for the ride. Understand? Okay. And we're also using t in this problem instead of x. That's just because we may as well mix it up, right? We have different variables. Let's just use t this time. Quick search through the Rolodex. This is not power of t. This is not a formula I know. Basic U substitution? Just a basic substitution. How about t squared is u? What's the derivative of that? 2t? I have beta t. That's off by a constant, but it's inside of a function. Remember, you could be off by a constant, but you could never be trapped. Your derivative can never be trapped, and it would be trapped here. That make sense? Yeah. So you don't get to do this. So let's think through this. The integration by parts, I'm going to pick one of them to be u, the other one dv. And in the new integral, I'm going to have the derivative of u and the antiderivative of v. So what would we want to choose here as our u? What would you like to take the derivative of over in the new integral and it become nicer? Probably t squared, right? Because if you do t squared, when you take its derivative over here, it's going to be 2t. It's still there, though. And what about, what's this thing going to become in the new integral? Like some sort of sine, right? So we're going to have like a t and a sine. Then you do it again. You do another integration by parts, and you'll kill this t off, and that sine will go back to a cosine. Two integration by parts is going to be what's required here. So here we go. You can look at it this way. If I run integration by parts, if I run one iteration of integration by parts on this, I'm going to pull the power of t down one by one, right? If I run the iteration of integration by parts a second time, that 1's going to go down to a 0, which means the t is going to vanish. The cosine is just going to switch back and forth from cosine, sine, cosine, sine. That's what's going to happen. All right, u is t squared. dv is cosine beta t dt. I'm really liking this class today. I like integration by parts. Did I tell you I'm thinking of teaching differential equations soon? Did I tell you all that? So I'm working through, what I'm doing is I'm going through the textbook right now, and I'm just doing all the homework problems, right? And I'm recording myself doing them. And I'm in this one section right now where I think almost every single problem I've done has required integration by parts. At somewhere in the problem, this has been in there. So it comes up a lot in differential equations, and if you're an engineering major, you're going to have to take engineering analysis, which has differential equations. So just start to become, you're going to be intimately connected to integration by parts. You're going to love it one day, all right? V, let's go du. What's du? 2t dt. And what's v? Careful here. 1 over beta, good. 1 over beta sine beta t. Good, so we're recognizing that beta t is like 3t, right? The antiderivative would be 1/3. All right, good. And now we get our nice little formula. This integral is equal to t squared ultraviolet. Oh, I should have put the 1 over beta out in front of it. You don't have to, but, and then sine beta t. That's ultraviolet, right? This times this. Okay, minus my new integral. I'm going to leave a little space out in front of it because I might want to pull a constant out. What will my new integral be? This thing times this thing, right? Let's get all our constants out. 2 is a constant, right? 1 over beta is a constant. So I'm going to put it as 2 over beta out here. And then what's still there? T sine beta t. And don't forget the all-important dt is still there, right? So we've taken this expression that had a t squared in it. We rewrote it. We've got an answer. And then a new integral. Now it's just t. We're going to do integration by parts again on this. Okay, so we want to kind of visualize that this right here is like in brackets. And there's a negative 2 beta in front of it. Now I'm going to go figure out what that bracket is. And that's going to be separate work that I do over here. I'm doing this integral t sine beta t dt. You make up a new table for integration by parts. U is what? T. dv is sine beta t dt. I'm pretty sure that's off camera. It's pretty close. And then du is dt. And v is, what is v? Yeah. Negative, right? We're going to have a negative. Let me just move this over so it's on camera. Sine beta t dt. And this will be, you said what? Negative 1 over beta cosine beta t. There we go. Yes, because that new diagonal doesn't have t anymore, right? And that's what I want. So just this piece, just this integral, I'm not even looking over there right now. Just this integral becomes negative 1 over beta t cosine beta t. That's ultraviolet. This times this. This times this. Minus integral, left a little space in front. Now my diagonal. And so what can I pull out of there? Negative 1 over beta. So can I go ahead and just make this a positive 1 over beta then? Would it be safe to say that there's plenty of room for error here? Yeah, I think so. And then what's still in here? Sorry, we pulled the negative 1 over beta out, made it a plus. We have cosine beta t dt. And that's the goal. I wanted to get rid of that t, so I just had a trig function there. And now this is negative 1 over beta t cosine beta t plus 1 over, 1 over beta, sorry. 1 over beta, and then now I need the antiderivative of that, which is 1 over beta again, sine beta t. This is just what's in there, right? So now I start putting it all together. 1 over beta t squared sine beta t minus 2 over beta bracket all of this crap. Negative 1 over beta t cosine beta t plus, can I make this 1 over beta squared? Okay, 1 over beta squared sine beta t and bracket and then plus c. One final step would be to distribute the negative 2 over beta through. Yeah, let's go ahead and do that. I mean, you're technically right. This is done. This is complete. But, I mean, we've come this far. Let's go ahead and distribute, all right?